Welcome back, Trinity Classical Academy. This is Mr. Bourgeois. I wanted to point out a fact first before we begin, like I do sometimes, that you are free to, I'm going to do this in cursive, skip videos, but not practice problems. How's that? Feel free to skip videos, but not practice problems. If you can read and understand the concepts by yourself, if you can do the guided practice and work through the examples and you understand what's going on, go ahead and do just the practice problems that I assigned in the lesson plan. Because that's fine. If you feel like you enjoy the extra explanation, if you enjoy my jokes, if you just enjoy the sound of my voice, whatever your reasons are, you certainly can listen to the videos. But I want you to have the freedom to just get your stuff done if that is your desire. Zip, 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 zip. All right, so right now we're on page 279. If anyway you want to leave and stop watching the video now, I will give you that permission. I'll wait. Okay, good, you're all still here. So, understanding probability models. Randomness is a central concept to the idea of probability. All the random phenomena have one characteristic: they yield an outcome that is unpredictable. A probability model consists of sample space of outcomes, events, and the probabilities of these events and outcomes. All of the outcomes of a sample space and their probabilities can be presented in a table or graph. Such presentation is known as a probability distribution. A probability model is used to estimate and predict the occurrence of events. So when we develop a uniform probability model, it's when all of the outcomes have an equal chance. It's rolling a fair die, it's tossing a fair coin. There are different outcomes and they each have an equal likelihood of occurring. Turn the page. Nope, not that. That. Ah. So we're looking at example 13. Example 13, so if you grab a random disk or a counter, I guess, out of a bag or something, what's the sample space? The sample space is yellow, red, blue, green, black. I know that because the words are printed underneath the colors. What is the probability of a counter being, of any particular counter being selected? Since it's random and every disk has an equal chance, there's equal chance of picking green as there is red. It's a 1 in 5 chance. You see that? And view the bottom of the page. You can see they plot out a probability distribution. That's what it's called, a distribution. So when you say construct a probability model of selecting a counter of a particular color, you use the bar graph to show the probability distribution. Now, that takes up a lot of space in the book, but it really doesn't take up a lot of time on the clock, does it? So now we're doing page 281. Guided practice number 1. Did we start the numbering over again? I thought usually they do, they keep the numbers going in sequence from the previous one. Whatever, we're doing guided practice number 1. Pause the video, see if you can do it, and then watch me do it and be amazed. Or don't. So, guided practice numero 1. There are 8 tiles in a bag, letters from S to Z. June randomly picks a tile from a bag. So basically this is asking, how well do you know your alphabet? The sample space is the letters from S to Z. Those are the possible things that could happen from the trial. That's the sample space. So the sample space is ST. Here, let me get it up here. So this is number 1A. The sample space is, we do this little jurly thing. S T U V W X y, z. Another little swirly dirly. You see sample space equals that. Making the sense? And then 1b, because there are 8 outcomes, 1b, the probability is 1/8. If you want to do that in a percentage, feel free, it's 1 divided by 8. Construct the probability model. So your probability model is going to be a graph. Sorry, not a graph, I mean a chart. It's going to be a chart. I guess I'll have to draw that. So 1b, please really fast forward this because I would not want to watch myself draw. So we have letter and then the probability. Woo! So the letter and the prob, there's S, probability is 1/8. There's T, probability is 1/8. And so on. That is the answer to C. The answer to D, you do it in a graph. Let's do it in a graph. So D, here's the outcome on the x-axis. Oh, we should call it letter maybe, huh? We can call it letter. And so we have, and then we have the prob over here. The prob here is 1/8. And basically every letter should go up to that line, right? So we have S, T, U, and you can put it down here, S, T, U, V, W, X, Y, Z, etc. That is the answer, guys. Well done. All right. That's how you do the graph, the probability as a bar model, right there. And this chart again is itself the probability model. It's the probability model in a chart. You can graph it in a bar graph. Oops, wrong way. Zip, 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 zip. All right. Murder that. Got it. All right, so blue box. Write the probability of outcomes in a uniform probability model. If the sample space of a uniform probability model consists of n possible outcomes, and the probability of each is 1/n. Let's look at an example. So this means that there's an equal chance of doing any of the outcomes, right? So example 14. Jane, Mark, Jason, Ruth, Albert, Kenny, Chloe are students. A teacher randomly picks one. Sticks in a cup. We already know that this is not a uniform probability because if Alina was there, her stick would have a greater chance of being pulled. So explain why a uniform probability model describes this situation. Well, the explanation is this, because there's an equal chance of drawing any of the students, any given student. So what is the probability that Ruth is chosen? Well, the probability that any student is chosen is 1/7, so then Ruth is also 1/7. Turning the page. Zippity bippity das vidanya. Actually, I feel like it's... Oh, if A is the event that a girl is selected, find the probability of A. We're assuming that Jane and Ruth and Chloe are girls. So since there are 3 outcomes favorable to the event, then there's 1/7, 2/7. I'm going to keep this going here. And 3/7, because there are 3 girls. You see that? This is important. This is a little more difficult to pay attention to. So 3/7. Because there are 3 girls out of 7. Does that make sense? I think it does. Guided practice, guys. Let's do it. Hold up. Wait a minute. Nope, not you. Go away. We're doing the guided practice. Pause the video and do it. Guided practice numero doso. Pause. pause the video, do it. Here we go, yeah. A number is chosen at random from the list. Explain, you don't have to write this out, guys. Explain why a uniform probability model describes the situation. Because each choice has an equal chance of being chosen. That's why. What is the probability of choosing 25? 1 out of 10. There are 10 numbers that could be chosen. This is B. Number C. T is the event of choosing a number that is a multiple of 3. List all of the outcomes favorable to T. Well, we have to look at the list. What's divisible by 3? Here they go. So C, the answers are 12, 21, 45 und 48. Yeah, you know, I can tell I'm getting bored when I start speaking German. Actually, I speak German just anyway sometimes. 48. I think that's how you say it in French. 48. Quator. I don't know. I forgot my French pretty good. All right, D, find the probability of T. The probability of event T equals 4 out of 10, but we want to simplify that down to 2 out of 5, or 40%, or you could do 0.4. Either one of these is fine. You win! Congratulations. All right, since that was easy, let's keep going. If it wasn't easy for you, I'm sorry that I called it easy. Zippity bippity 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 bippity. All right, develop a non-uniform probability model. So, if a uniform probability model is equal chance of anything getting picked, then non-uniform is not that. Let's go up here. Murder. So, example 15. An art teacher has a bunch of colored pencils. There are 3 yellow, 6 orange, 2 green, and 4 brown. Those are colors, I reckon. She randomly chooses a color to give to a student. Okay, I would say this differently. I would say she randomly picks a pencil to give a student, not a color. By being careful with my verbiage, I am clear that I'm not picking a color randomly, I'm picking a pencil randomly. Define the sample space. There are 4 different color outcomes. So the sample space is yellow, orange, green, brown. Those are the possible outcomes. You can pick a yellow, an orange, a green, or a brown. So those are the color outcomes, but the sample space has 15 different outcomes. They say that because it's the total number of pencils. You could pick the first yellow pencil, the second yellow pencil, or the third yellow pencil, or the first orange, the second orange, third, fourth, fifth, sixth orange, etc. So they say the sample space has 15 outcomes. So then what is the probability of choosing a brown pencil? Let B, so now we're on page, the other one. Let B be the event of choosing a brown pencil. So how many brown pencils are there and how many total outcomes are there? There are 4 brown pencils. Zikes. 4 brown pencils out of 15 pencils. There we go. So the probability is this, 4/15. Can we simplify that? No, we can't. So what is the probability model? A probability model. Look at your book. It says the probability of picking a yellow pencil is 3/15, an orange pencil 6/15, a green pencil is 2/15, and a brown pencil is 4/15. Notice they all add up to 15. Let's look at that. They should. All of your probabilities need to add up to 1. Otherwise, you did it wrong. I promise. 3 plus 6 plus 2 plus 4 equals 15 out of 15. They should add up to 1. Always, always, always. So enthusiastic math student says you can use the table or the graph to compare the probabilities. For instance, the probability of getting orange is greater than the probability of getting yellow. Yep, because the number is bigger and the bar is longer. Turning the page. Pause the video, do guided practice number 3. All right, good job. You did guided practice number 3. The answers are, all right, so we're looking at T. Define the sample space. For different flavor outcomes, the flavor outcomes are peppermint, raspberry, chamomile, and blackberry, but the sample space has 10 possible outcomes. There are 4 different peppermint outcomes, 2 different raspberry outcomes, 3 chamomile outcomes, and 1 blackberry outcome. So that's the sample space. Number B, what is the probability of picking raspberry tea? Well, there are 2 raspberries out of 10 possible outcomes. So B, 2 out of 10 equals 1 out of 5. Or you could say 0.2. Or you could say 20%. And we all know my favorite is percents. I love percentages. They make it just, you know, nice. Unless we're talking about pi, in which case don't give me 20% of a pi, give me a fifth. Construct the probability model of the tea bag, then use a bar graph to represent the probability distribution. Here we go. Wrong one. All right, you may so skip this if you want to, but if you're going to do it on the checkpoint, you're going to need to know how. So watch how. So here is the T. Here is the prob. So the T is peppermint. The prob is 0.4. Then there's razzle dazzle, the probability of 0.2 or 20%. There's chamomile. Hi Cam, how you doing? 0.3. Then there's blackenberry with a probability of 0.1. Do these add up to 1? I sure hope so, otherwise we know we did it wrong. 0.4 plus 0.2 is 0.6, plus 0.3 is 0.9, plus 0.1 is 1.0. We did it, you guys. And then you have to graph it, because I said so, mwahaha. So then the graph will look like this. And there's, up here we have 0.4, or 40%. 0.1, 0.2, 0.3. Boop. And so the peppermint goes all the way up to here. That's pep. The raz goes up to the 0.2. The cam goes up to 0.3, or thereabouts. And then sad little blackenberry. Maybe he's not sad, maybe he's like, I'm rare. Why is he a boy? I don't know. Raz is a girl, blackberry is a boy. Cool? I think so. Alright, I hope that you've rejoined us if you've skipped my demonstration of how to draw a bar graph. Because now you're going to watch my demonstration of how to erase a whiteboard. Now then, folks, we bees on example 16, page 284. Hopefully you guys don't get too thrown by my page numbers if my page numbers are sometimes wrong. What is the probability? Find the probability of events in a non-uniform model. A number die was made incorrectly at the factory. Whoops. The probability of rolling a 1 with this die is a 4th. Each of the other 5 numbers has an equal probability of being rolled. Find the probability of rolling a 4. Well, I feel like a bar model would work really great, or a pie chart. Pie charts are like bar models except circular. You probably already knew that. So what's the probability of rolling a 4? Well, we know that out of all of the probabilities, I'm gonna bar graph it. So here's all of the possibilities. We know that 1/4 of those is the probability of a 1. So this is 0.25. I'm going to keep it in decimal form because reasons. So then the rest of this is 0.75. And it's divided up into 5 equal outcomes, right? Let's try to do this in fifths. I'd get 5. 1, 2, 3, 4, 5. Okay, these are equal. I know I didn't draw them super the best, but there's a 2, there's a 3, there's our magic number 4 that we're looking for, there's a 5, and there's a 6. All right, so we're looking for 0.75 divided into 5 equal parts. So 0.75 divided by 5 equals 0.15. So if you are playing a game and you're trying to roll high, you're going to be very sad that you're rolling ones a lot and your character is getting killed. So then it says construct the probability model. Guys, turn the page. Or look at the other page. You're not turning anything. We're on page 285. It says the probability model is going to look like this in a chart form. And then it says C, what is the probability of rolling an odd number? Well, let's highlight our odd numbers here. Let's use Jello. Odd, odd, odd. So we know that this is 0.25 plus 0.15 plus 0.15. So the odds of us rolling an odd number are 0.55. Make sure, see that caution sign? All of your probabilities need to add up to 1. That is a universal truth. Good job, guys. Let's pause it and do guided practice number 4. I'm going to peek ahead a bit. Guided practice number 4. All right. So the answers are, the probability of getting a letter N is 1/3. The probability model is going to be a chart thingy. And the probability of selecting a card with a consonant is going to be 2/3. Here we go. Because how many N's are there in the word beginning? You select a card at random. So we have 3 N's. So here's A. So we have 3 N's, and B, E, G, I, N, N, I, N, G. There are 9 letters, right? So the probability of N is 1/3. 1/3. There we go. Q, probability model. So here are the letters. I know I didn't cursive that L. Here's the prob. Now I'm kind of sloppy when it comes to this whiteboard because it's very difficult to hold your finger vertically, but I expect you guys to be neat. And I know I'm not checking your work, but you're doing it for the Lord Jesus anyway, and neat work counts. So I know I fixed my L. I think that's funny. All right, here we go. We got the letter B. Boop. We got the letter E. Boop. We got the letter G. Boop. We got the letter I. Boop. We got the letter N. Boop. Those are all the different letters we have. There's only one B. There's only one E. However, there are 2 G's. There are also 2 I's. And there are 3 N's. Do these add up to 1? 1/9. 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 ninths here, guys. Our chart looks good to me. What is the probability of selecting a card with a consonant? Let's highlight our consonants and take a look. This is a consonant. This is a consonant. And this is a consonant. So we have 1 plus 2 is 3/9 plus another 3/9 is 6/9, which is 2/3. The answer is so this is B, and then for C, that would be what did I say? 6 over 9, which equals 2/3. Boom shakalaka. If you did 66.7%, I would say that is a wonderful answer. That's how I would do that. All right, now sit and wait while I erase the board. Talk amongst yourselves. Oh, sorry. Soul-crushing loneliness. Not really soul-crushing. What a friend we have in Jesus. All right, so we're looking at example 14. Oops. 14. No, 17. Some out of me, huh? Example 17. Develop an experimental model. The data below shows heights in inches of 20 players of a junior basketball team. Look at all those heights in inches. Group the heights into intervals, 4 intervals. So they say put 4 intervals down, 50 through 55 through 60, 60 through 65, or 2, I should say, up to 55 up to 60, 60 up to 65, 65 up to 70, and 70 up to 75. It says the interval 55 to 60 includes heights that are greater than or equal to 55, but less than, not equal to, just less than 60 inches. So then you plot them into that chart. You see how they did it? Turn the page. Now, find the relative frequencies of the 4 intervals. Well, the first interval shows up about 5 out of 25, which is a fourth of the time. The second interval is about 0.35. The third interval, 0.25, like the first. And then the last interval, the biggest interval, is 0.15. So the probability model is shown below. They just convert those relative frequencies straight up into probabilities. So represent the probability distribution in a histogram and state which type of probability model you have drawn. You have drawn... What does it say? State which type of probability model you've drawn? I don't know. Let's see. So since heights, okay, that's why. So it's a histogram. A histogram is a that's what they mean when they say the type of probability model. It is a non-uniform probability model. There you go. And we call it a histogram in this case because we're using intervals. Histogram. Intervals, because it's continuous data. Continuous data is like, how tall are you? Two people can be like, you can be between 65 and 66 inches. You can do it on a number line. How's that? You can do it on a number line and you can have non-even numbers. You can have non-whole numbers on a histogram. Does that make sense? So that's why it's called a histogram instead of a bar graph. So that think math, the bar graph would be something like categories like chocolate chip or sugar or snickerdoodle or Neapolitan, chunky monkey, or what's another weird flavor of ice cream? Rocky Road, Moose Tracks. Those are types, they're categories. You wouldn't call that a histogram, you would call that a bar graph. Phraseology, right? Okay. We shall move over to the next page. My voice cracked and I tried to hide it behind a silly voice. It just cracked. I'm in that awkward stage where a boy becomes a man. Had it practice 5. Dude it. Red pen. Pause video. Ah, good job. You did it. Good job, you guys. The data shows both the heights in centimeters of 25 tomato plants in a greenhouse. Group them in intervals. Good night. So the intervals shall look like. All right, here we go. Here's the interval. Here's the prob. All right. I should say frequency, not prob. Eventually we'll call that a prob. The frequency. All right. So we got 80 to 90. Shows up 4 times. I'm just copying straight out of the answer key. Guys, this is an intense problem to solve. It's very labor intensive. 4, 100 to 110, 7. Nope. I feel like I've already started. I might as well finish, right? 110 to 120. This is going to be a histogram again because, guys, these are continuous data, not categorical data. What are we on? 120 to 130. Then here we got 130 to 140. You could also just say 130 plus and just call that good. That's how I've generally seen histograms go. 5 of them's and 2 of those. Let's zoom it out, why not? Boom. So this is what your dealie should look like. And if you draw it nice and neat and pretty, like Alina probably did. Good job, Alina. Well, you got picked on a lot today. And Grace. Grace draws really pretty stuff. Don't feel offended if I don't recognize you. I'm trying to think about who draws really pretty work in their practice things. A lot of people draw really, really pretty work. I don't want it anyway. Moving on. Don't have hurt feelings, please. All right. So then, for B, you're going to convert these frequencies into probabilities. I'm just going to do this for the sake of simplicity because you don't want to watch me sit here and write stuff, right? I suppose I could have done it in advance and then just plopped it into the picture, but why would I make this any easier on you? All right, so 0.16. This is also 0.16. Oh, you know what I also could have done? I could have just done this instead of erasing. Let's try that. The Wayback Machine strikes again. All right, so now we have prob. So 0.16, 0.16, 0.28. My decimal points don't show up very big. 0.12, 0.20 or just 2, and 0.08. Do these add up to 1, y'all? Let's checker it out. 0.3, 50. Do they? I don't know. Let me try this again. I did it in my head and I didn't come up correctly. Let's see. So 40. Oh yeah. I did that wrong. Okay, so 48 plus 16 plus 16. No? Wait, what? All right, one more time. Okay. Third time's a charm. I came up with 1. Oh dear. These add up to 1. Okay. Letter D, if a plant is selected at random, what is the probability of selecting a plant whose height is greater than or equal to 100 but less than 120? Let me undo that highlight I just did. So for number D, I hope I got you in the habit of calling letters numbers. Hopefully I did, and hopefully it sticks with you forever and you'll remember me by it. So we're looking for a probability of a plant that is greater than 100 but not greater than 120. So what are these? So we're looking for this range right here. Should be a distribution range. So the probability should be, we add these two numbers together, 0.28 plus 1.12 equals 0.4. I like it percentage because it's great. So if you pick out a plant, if you're looking for a plant between 100 inches or centimeters or whatever we're doing, inches would be like crazy. 100 centimeters and 120 centimeters, you got a 40% chance of grabbing one at random. There's a hands-on activity, you guys. Do it if you want. Otherwise, call it done. You've been beautiful. You've been great. Love you guys. Bye-bye.